Hello, um, this is Jacob. I'm replacing many of I'm replacing several other speakers that should have been happening today for the Python meetup. Typically, we arrange the Python meetup. We have several organizers, and we arranged with the Python meetup to be as regular as possible. However,
Hello,
um,
this is Jacob. I'm
sorry,
replacing many
I will
of
have to keep echo down. Give me a
I'm
second.
replacing several other speakers that should have been happening today for the Python meetup.
Okay, so um, yes. We're hoping that to have a Python meetup today. However, there were several incidences that kept it from happening, and it started a long time ago with South by Southwest, where we kind of lost our regular location, but we were trying to compensate, and we indeed got a different location. However, then the coronavirus scare happened, and we decided that maybe it would be better for all of us to go online rather than meet in person. So it seems prudent today. We don't know how long the situation will continue. So also today is kind of testing our ability to stream information and continue this meetup while doing it online. Um, we try to get several people. Uh, uh, we try to get several people interested in doing the meetup this time, but unfortunately it wasn't possible. There were several problems. So I will try to compensate for not having the regular meetup today, and all of our organizers of the meetup, we always have some kind of backup talk in case the meetup got canceled. So today I'm going to talk about something that is related to the situation that we're having today. Um, I'm a computational disease modeler. I model diseases and healthcare related issues. Um, and usually, I go to this meetup meeting once a year at the NIH. Um, this meetup was supposed to be happen next week, but it was canceled as well. But actually, it was postponed. So the talks as well that we were planning today for the meetup Python meetup today, we postponed them, and instead we're having this live stream. Um, it will be hard for me to communicate with you in the live stream, so I will be talking, and every once in a while I'll look if there are any questions. I'm not sure I'm going to capture them all because I'm trying to handle several systems here. Um, there are several technical difficulties in having everything, but uh, if you can post questions online either on the meetup page or if possible on the YouTube channel that you're watching. I don't know if it's easy or hard for you, but if you can post questions there, I'll try to answer them. If not during the talk now, maybe later on. I didn't measure exactly how much time I'll be talking about the issues, but I'll be sort. I may have an assortment of topics that come together and explain approximately what uh, computational disease modeling or actually healthcare modeling, what it can model and things like this. And I will show you some of my own work that I've been doing throughout the years, and I'll be showing you some Python, not actual coding, but some of the things, mostly the things that I've been doing, or all the things I've been doing, they are Python related, and you'll be able to see them. Some of them are actually available online. You'll be able to use them. So I will now switch the screen so you can actually see what I'm talking about. And give me a second. And here we go. So I'm now sharing my screen. You'll see me in the little corner on the side. Um, this is the meeting I go to at the NIH. I try to do it every year. Um, doesn't always happen. This year it's been postponed. Um, and In this meeting, usually many computational models from all around the world gather, mostly from the US, but also from other places in the world. And They talk about multiscale modeling and computational modeling, and recently also machine learning. More and more examples that you see there are Python related these days. Uh, and One of the things, activities that we're doing in that multiscale modeling consortium was uh, uh, dividing into working groups, and there are different working groups. There was high performance computing working group. There's a working group about sharing models. I was involved in a working group called Population Modeling Working Group, and we actually have a website. You can find it through SimTK. I will send you some of those links later on in some of the channels so people can follow me later. But for now, I'll try to give you an explanation of what we were doing in the population modeling working group. Um, uh, we try to uh, give give an understanding of all what were the people modeling using by creating a map of all modelers, and we actually created this map. You can find the links to this map here. Let me show it to you. This is, you can see here all sorts of computational modelers from all sorts of universities, institutions, uh, and you can see what they were modeling here. And there's some links. Here it's one paper, but actually they wrote more. When you assembled all this information, there are many more examples. And then you can see the summary of methods, computational methods that are using. Um, you can see people here will be working in the epidemiology field or public health. Some of them will be working on managing disease spread. Some of them will be discussing resource planning, meaning how to organize a hospital, for example. And all of this involves modeling. Some of them will be predicting drug effects. Some of them will be predicting the risk of something happening, let's say heart attacks. Um, some were actually modeling ecosystems, mostly animals of ecosystems, trying to model all ecosystems. Some were trying to model disaster and emergency response. Some were testing all sorts of theories, mostly philosophical, but you can test computationally, and some were involved with behavioral modeling, mental health modeling, things like this. And some were developing tools for either computational modelers that do healthcare. And you can see we had quite a list of modelers. We took several years. We had several conferences, and each one we tried to assemble several of those modelers that gave us summaries of what we were doing. Let me show you some of those examples to give you an idea of what kind of modeling is happening. So I'm going to skim through those. All of those links are available online in under SimTK. And by the way, SimTK is a website that is handled by Joy Koo in Stanford, and it has all sorts of computational models inside. Um, Many of I'm going to skim through some of the examples. I'm not going to mention exact names. You can later look at them if you're interested in more information. And there are links and papers where you can find even more information and more information about those. So this is like the summary of the summary of the summary. Uh, Olaf Damon's group, they're in Tufts. They are trying to model populations of and usually he works with infants, so he's trying to model infants, and he's trying to make the simulation match whatever was published in some papers, and this is where the computational models are trying to explain what's happening, also phenomena. Um, the examples of what you see here is a population a pyramid. It shows population when women, how many of by ages. A lot of population modelers do this, and there's some nice animational effects, but won't show them now. Some modelers like Tony Hunt, they model what's called multiscale models. They start from the molecules later build up to the cells and into the bodies itself. And typically, they're trying to model lots of drug effects, but not always. Um, there are people who will work with social networks of animals, actually. Um, there are people who are interested in natural disasters, how effective it will be on populations, and they're trying to model it. Um, in natural disasters here, for example, are hurricanes, not like viruses like we have today. Some people model this as well. So, for example, infectious diseases. So people model those, and this is one example. Um, uh, People model tumors, cancer tumors. Um, People model sexual transmission of diseases. And look for the entire population and connections between the people and how it's spread and not. Uh, Again, impact of all sorts of disasters. Uh, Mental health modeling. Some people model mental health modeling. This is Steve Leff. He's from Harvard. Model this. I'll skip some of my slides because you'll see them later. Some people use something called discrete event simulation, where you actually simulate events happening and put queues of events. And for example, people standing in line in let's say a hospital waiting for some resource, let's say an MRI or some other or a doctor, and you're trying to optimize such that people will wait as less as possible, and the system will be optimal. Many of them use discrete event simulation, and the idea is to make the healthcare system much more efficient. Um, and some people model drug resistance. And exoskeleton and skeletons actually are being modeled as well. Actually, SimTK, if you go into SimTK, a lot of it is to do with a lot of the open simulation models are there. So, and many of them are modeling the skeletons and dynamics involved. So this is like some of the examples. This is only one of the presentations we had with the example of example. Later we did more. I'll mention this one because it's highly related to the things that we're knowing now. For example, how do people model the spread of a virus or infectious disease? Usually it has to do with a set of differential equations called SIR, and there are several variations of those. And one person who models them is Robert Smith with the question mark. It's not a mistake. The guy actually, if you go to his website, and you will find out he actually writes books about modeling zombie epidemics, mathematical modeling, and which is kind of interesting because it's kind of an infectious disease that didn't happen yet. Just like the corona, we didn't know about it up until a few months ago. Well, this is how you model those using those differential equations. The guy is not answering to emails now. These days, he's very busy. He'll probably after all of this comes down, he'll respond. And interestingly enough, this is not Robert Smith of The Cure, so it's a different Robert Smith. Anyway, we were actually handling this population. At some point, we were cooperating on this population modeling working group. This is why I mentioned his name. Um, let's go to other examples. People model HIV drugs, how they affect the body. A lot of the modeling of drugs is something called PKPD. A lot of them are differential equations, but you do also need to do some stochastic simulations there. Um, a lot of the problems have to do with the models, that a lot of the parameters in the models are unknown. So a lot of people are working on parameter estimations. Um, there are people who work on ecological questions, uh, the effect of toxic chemicals, also how they affect the populations. Again, you can see differential equations being used. Um, some people, a lot of people actually study something called cost effectiveness. Um, uh, it's ability. It's actually they figure out how effective a certain treatment it is compared to compared to the cost of the treatment. Actually, some governments actually put some attention to how cost effective things are, and they approve or disapprove drugs looking at this criteria. Specifically, I know that was true for the UK. They had an institute called NICE, National Institute for Clinical Excellence, where they were looking at cost effectiveness of the treatments that they are making. Um, uh, uh, Resource management, sometimes you have to look at the population of your experts to see how they treat um, your populace, and some people model that. PKPD, I mentioned, this is drug effects. Many people study this. Um, you will see some more examples of this later, but Carl Ash is from Chicago, actually Illinois, University of Illinois. Um, he is looking at different risk equations, the probability of having certain conditions. Here is an example of people having a heart attack, and he's studying them. And actually, he's actually studying something that's very important to hospitals, which is after you have a heart attack, what's your chance of readmission? Meaning you went to the hospital, you got treated, you got better, but all of a sudden you go back to the hospital. So hospitals are trying to reduce this readmission, and therefore they need models that try to predict what will happen. Um, uh, we have uh, cancer cancer modeling here, uh, and we have um, more modeling of drugs. Um, some people use techniques of fuzzy logic. This is very, very unusual for population modeling. Um, Specifically, this is like for animals, like global jellyfish. But some of the techniques that you see are being used are not traditional, like PDEs uh, or some other differential equations. Um, some people use agent-based models. I'll just give you an idea of what agent-based model is. Is you model agents, and each agent does several things, regardless. And some those major agents sometimes are allowed to interact. And then you set them to the world, and they interact with the environment and with each other. Each agent can be like a simple algorithm or more sophisticated algorithm that allows them to interact. And this is how you model whole populations of them. Today, you have a lot of computing power, which is cheap, and therefore those techniques are becoming more and more common. I'll give you a few more examples of population modeling, and then I'm gonna. Those are examples of what other people that I know or interact with are doing. But there are many, many more examples, and I'm going to switch little by little to after I give you some idea of all the world of modeling that at least I'm familiar with to some degree. Um, I'm going to zoom into things that I've been doing in the last few years, and you'll see more and more Python. Um, some people who are, especially those who model sexually transmitted diseases, need to model how they pair the people and who transmit the disease, like who likes who, and therefore they might have a higher chance of transmitting the disease to those people, and so on and so forth. So the matching algorithms is part of population modeling. Um, uh, there is the concept of evidence-based medicine that's being used a lot, and the idea is use it. uh, use the actually facts that you know about, and then use techniques like Bayesian modeling to actually be able to explain those facts. Um, Chris Fonnesberg, he's no longer, and by the way, he's no longer at the University of Vanderbilt, or maybe he's adjacent, I don't remember, but um, he has now a much better job. To look him up to see what he's doing now. But he actually one of the contributors to one of the Python libraries, PyMC3, I think, which does Monte Carlo simulation, MCMC, Monte Carlo. Forgot the other two acronyms. Here, PyMC. Um, he has several very good people who even do machine learning. Should look at some of his blogs. Very interesting. Check out Chris Fonnesberg. He's a good Python guy. Um, he's on our side. I'm kidding. Uh, uh, there are people who do a lot of types of modeling, not necessarily one. So, for example, Danimin from Tel Aviv University does several of those uh, for population modeling. But he was working on vaccination, specifically some vaccination in Israel a few years ago, and they had some interesting conclusions they gave back to the government. Diabetes. You'll see much more modeling of diabetes. Diabetes is one of the problems of the modern society, and a lot of it is being studied. Just to give you an idea, um, population that has diabetes above age 50 is about 5% of the population. Above, say, age 60, it's about 10% of the population have diabetes. These are like rough numbers, but it shows you how bad the problem is, and it's a not nice disease. Jeff Schrager. Actually, if I'm mentioning Jeff Schrager from Stanford, you should look up his ELIZA page if anyone's interested in machine learning. But actually, he actually explains very well how AI can look at and help with diseases. The idea is that if you have many examples, then machines can learn from them quite well, and it's better than maybe clinical trials in a sense that the clinical trials you control them a lot and you don't see a lot of the information inside visible. I'm kind of explaining it in broad terms, and I may be slightly incorrect, but this is the best way to explain what he's doing. And he's not modeling air traffic control. He's actually looking at populations and individuals and figuring out what's happening with them. Uh, look him up. He does several very interesting things, and now he has a company. Felix Mekabana, he's from John Hopkins. He's modeling HIV. Also, a lot of drugs. What drug is more effective? We already talked about Kalash. Um, some people actually looking at populations and trying to model things like cognitive development. Michael Thomas actually does many more things, but this is one of the slides that he sent a while ago, so we use that. Um, Infectious disease modeling, and this is interesting. Marco actually was able to take multiple countries and put them and explain how well they can be explained by models, and you can see this graph here. Um, you'll see later I'm doing something somewhat similar for diabetes. Polio. Uh, this is in Israel. There was a polio outbreak at some point. So they modeled this. And uh, you will see later example, all of more examples. But when you deal with population modeling, you need a lot of examples of individuals, and you don't always have your hand on the data. Actually, data in the population modeling world is very hard to get because it's highly restrictive. Because when you give the information to your doctor, the doctor not necessarily they're actually disallowed to share it. And therefore, sharing your individual information with others is very difficult, and under very in most of the time it doesn't happen at all, and if it happens, it's very restricted. So to bypass this, a lot of modelers need techniques to generate fake data, population generation. Like think about the ability to generate all sorts of individuals that are kind of randomly, you generate them, but not, they don't really exist. There are several other uses for this, but several people work on this, and they also work on this not only uh, uh, for the purpose of modeling populations of humans. It can be populations of anything: cell phones, automobiles, uh, many things. Think about modeling a population of devices if you're doing IoT. So all of those things, Internet of Things. I mean, um, if you're in that direction, you'll need many. Uh, you'll need data that doesn't exist yet, or exists but you don't have your hands on it. So you need those techniques. So some people are working on this, and there's actually multiple people working on this. Um, um, uh, there's a large community of people modeling cells, actual cells, to see how the cell behaves and computationally figure out things within the cell. Um, oh, People who model again ecology and the extinction of things, of creatures. Um, um, oh, Again, evolutionary computation. This is actually, they're trying to figure out how evolution evolved. Like how does evolution work through many years by creating small little computational entities and following them. You cannot model things for hundreds of years or thousands or decades or much beyond, but a machine can actually, you can look at evolutionary you can look at evolution in a machine and like run the time much faster by doing all sorts of tricks. So many people are doing this, and some of those actually are useful, become very useful algorithms, like genetic or evolutionary algorithms. You'll see some examples later. Um, there are some people who model human behavior, um, uh, and again, data generation, another library. This one is for R, not for Python, but it's okay. R and Python are friends. Um, there's one more aspect that is important. If you create models, any type of model, how do you share them? So some people who are working on sharing models, and there's specifically in the system biology community, system biology created something called the biology markup language. They're trying to standardize things, but they are not yet a standard. However, they are a good spec, and you can actually transmit disease models with it. Meaning, not transmit disease, but when you create a disease model, you can actually communicate it to someone else using a different software. Think about it as passing a Word file that has all of your computational knowledge within it, and someone with a different software on the other side opens it using a different kind of software. So it doesn't have to be Word; it can be Office, LibreOffice, or one of the Google interfaces that opens docs. But now the document is not a word processing document; it's actually um, a model that you can do things with, and you can do many things. So we did some population modeling with this a while ago. Um, so I'll go back to the matrix, and now all of those examples that I showed you before in this matrix now hopefully make more sense. So this is like the world of computational modeling, and a lot of those people do. I met at the Multiscale Modeling Consortium, where again, multiscale is where you actually model in different scales, and the idea is that you transit one scale to another. For example, from the atom scale to the molecule scale to the uh, uh, organ cell to the organs, or to actually to the cells, and then to the organs, and then to the entire organism, human, animal, and then to populations. And the idea is to traverse all of this. And when you have all of those working together in the future, we might be our models might be doing much more. So I've been working. I've been going to this meeting for many years now, and met a lot of people, and I always try to present something nice there. Um, And by the way, I recommend if someone is interested in those topics, this is a free meeting, and I'm going to show it again. This is happens about every year. Highly recommend for people interested in computer in healthcare modeling, and I mean computational modeling, and specifically multiscale modeling. The meeting is at the NIH and it's free. Highly recommended. But they also have working groups, and you can actually explore and interact with people throughout the year. So. It's a very good project, and I like it so much. So I figured I'll tell you, even though it's postponed next week, they will be streaming live, so you can actually go and see what they're doing, streaming like what I'm talking about. So again, go to imagwiki.nibib.nih.gov, and you'll get much more information. And uh, it's your government actually working and doing very good things for you. And those who are seeking knowledge, this is a good place for knowledge. You will learn a lot. Um, so I've been modeling. I'm going to transition and explain more and more what I'm doing, except from running around and trying to organize the Python meetups here. We, by the way, have multiple organizers. Uh, I'm one of them, and I'm today's backup. Next time when we have a cancellation, someone else will step in and give their backup spiel. Um, so I've been doing this for a long time, for over a decade now, and I'm starting to develop ideas that go in the direction of uh, compute machines at some point can replace some human tasks that humans do repetitively, human reasoning tasks, even. I'm thinking about something big as having a doctor on your smartphone that is always with you all the time. And in fact, we already have things like this already, but I'm always comparing it to what happened with chess. It took about 50 years from the beginning of chess till from the first chess program to when Deep Blue once against the world champion. It's about 50 years. Driverless cars today, where people are talking about them doing some things. Well, the first attempt started in 1977. In 2018, like 2 years ago or less, Waymo, this is basically Google's offspring, uh, they they commercialized after driving 10 million miles autonomously. So think about it. This is a few decades, and you're able to achieve this. I started assembling what happens with the computational modeling world, and I'm talking with the healthcare modeling world. And I noticed that there is advancement, and I'm writing some of the key models that I'm familiar with, but there are many more. And I believe that within a few decades, we will have smartphones that will take over some of the reasoning tasks the humans are doing, and will do some tasks much, much better than humans. Just like today, computers do some things better. It's a long time until this will happen. However, I will show you some of the things that I've been doing the last several years to give you ideas of what machines can do even now and how good or bad they can do it. Today, I cannot say that machines are doing things very well, but things are advancing and advancing fast. So I'm showing you a presentation from AnacondaCon last year. You can actually look it up. But I'm going to skim through it and give you a new information that I accumulated last year, or tell you things I didn't tell there, so it'll be more interesting. For example, recently I actually asked people, several experts, not a large survey. I asked them to predict how long it will take for machines to take over human reasoning tasks. And interestingly enough, the AI experts said that some things will be impossible for years and we don't have the solutions. While the healthcare people say, well, it's happening already. And they're thinking about the fact that now when you're sick, you Google what's happening with you. Even now, we're trying to figure out gather information about it. We go to the internet and we collect it. And the tools are becoming better and better and more available. Therefore, they're already replacing what the doctor was doing. And even now, today there are healthcare providers that you actually chat with the doctors. Um, think about it. This chat with the doctors in several years, you will not know whether there's a doctor on the other side or a bot. It will take a few years, it will take many years, but the more people who chat with those doctors and the more machines will see those chats, the the machines will come better and better and better in replicating what the doctors are doing and figuring out what actually was effective or not by looking at history of what happened afterwards. Things that doctors are hard for them to do. Think about it. They are stressed out because they see patient by patient by patient by patient. It is quite a hard task. They're like superhumans, but they are humans. They cannot read all the material out there. Machines can. There, every few seconds comes out a new medical paper. You later see, I'll show clinical trials. Also, there are so many of them, you cannot even follow what's happening. So I'm going to go ahead and I'm going to talk about several things you can do today with Python. Let's start with something simple. You can visualize, just visualize one patient. This is one patient and multiple machines taking information from that patient. The data is noisy. You can see all of those outliers here. So I took several algorithms, and this is very simple Python. Um, some some scikit-learn and some scikit-learn functions and several other functions that I wrote myself that are not very sophisticated. And I'm trying to figure out if a machine without anything sophisticated can figure out the outliers. And here you can see how you can do this. And more interestingly is you can actually go around and add some information and show it visually very nicely exactly what's happening. So you can show what certain algorithms are doing. So I was using Bokeh to visualize this a while ago. It's a Python library. Today, there are even more sophisticated visualization libraries. You'll see several of the examples later on. And I'm not showing you the most sophisticated stuff. They're coming out with new stuff all the time. It's hard to follow all the how fast the visualization is progressing. But forget about the visualization for a second. Look at how much information the doctor has to look. This is only one patient followed for a few hours, and this is information that's available publicly. Look at this is the time span, only a few hours, like less than a day, and there are multiple charts that the doctor has to follow. I'm scrolling and I'm scrolling, and there's more and more. Some of them are funny, like the only ones and zeros, and some of them have more information. Some of them are like that, where they're quantas of what's happening. And you can actually figure out from those things approximately what happened, and some of the information is assorted. There's actually many, many more pieces of information that is hard to visualize. But having one, being able to show them all, like lab results, monitor results, and flow sheet, all of them together and visualize them, if this can help the doctor and adding some cues on it, if this can help the doctor spend a little bit less time on of trying to figure out the charts and like the machine helping them, it's already great. But this is an example of what might be possible, just from visualization point of view. But I want you to capture the idea that how much information the doctor sees and how much information we want this information to be processed by machines. I'm going to switch to something else now. Um, we talked before on population generation techniques. So remember, I was talking about fake data. So there are techniques that can generate those. Actually, I have a tool called the microsimulation tool. It's free software. You can download it from my GitHub account. Um, and it will generate populations, it will generate fake data that matches statistics of real data that you know. So it will generate a bunch of individuals, and it'll do it through evolutionary computation. I'm going to explain later how it does, but basically it generates a lot of a lot of people and select a subset that matches the statistics you want. So if you need 10,000 people, it generates like 10,000 and selects the 1,000 that match best what statistics you wanted. And why do you need to do this? Well, population innovation is not trivial. You want to generate individuals who kind of have different parameters and like male, female, age, blood pressure, and so on and so forth. Some of them are correlated, but you also want to restrict age, like you don't want people under the age of 18. The minute you add all of those together, it becomes a difficult problem to generate a population like this. So you need to mimic this the population statistics. You need good tools to do it. Um, and one of the techniques that I'm using, and again, it's freely available under if you download Mist, um, the microsimulation tool. The way it does this is through evolutionary computation. Some of you know the idea of genetic algorithms. Well, evolutionary computation is a general term that includes also genetic algorithms and some other algorithms as well. The idea is that you generate many subpopulations of candidates. You score each one of the subpopulations. Score meaning how well they fit your population statistics. You give them a score. Then you select the best ones, you treat them as parents, and you create offspring using crossover operators. You also use mutation to create slightly different solutions, and you repeat the same process again and again and again for many generations. Eventually, you get a population that the best solution actually is much closer to the populations that you have. Sorry, to the populations that you want, the statistics that you're interested in. And notice you don't use real data, you use fake data that matches the real statistics. So this approach actually is very useful for something. I work for this with Olaf Daman. He's again from Tufts and from Anselm Bloomer. We published it about a year and a half ago. Olaf had the problem. He said, "You know what? I have the problem to see uh, how can I predict things within the population and without knowing much about it, but I do want to know how a specific treatment or drug can affect that population without knowing too much parameters, but I do know some constraints on that population." So his problem was, I have 617 infants. He knows the number of infants. He knows how some of them have experienced sepsis, and some of them get oxygen to treat them. Now, after that, he figured out there's an outcome. Some of them, after having those conditions, some of them develop something called retinopathy of prematurity, ROP, we'll call it. And he knows the percentages because he measured them in populations. But now, he also measured several correlations between those parameters. Specifically, he used odd ratios. It's a formula. So he knows the correlation between those. You have all those statistics about the population. And now he asks, you know what? What if there was a drug that reduced sepsis from 32% to less, or some sort of treatment that applied that will reduce sepsis? How much it will affect the retinopathy of prematurity? Now, notice there are only those few numbers that you know, and you need information or under such hypotheses. So this is a purely mathematical problem. However, it's not that easy to solve because there's distributions of those populations, and there are many populations that can match. So what we did is actually use something called population disease occurrence models. It uses evolutionary computation to generate many populations, and the, when we generate those populations, we match those statistics that he wants to match. And once we do it, we can measure the effects of things happening by assuming that some of the um, constraints that you have are biological, meaning they are not affected by environment. It's something that's biological. Under this assumption, you can actually calculate what will happen to some populations, and you can actually see that ROP will be reduced If you reduce sepsis from, let's say, 32% to 8%, like a quarter, how much will ROP reduce? From 47% to a range. There are many, many possibilities, and we studied all of those. But on average, it will be 4% reduced. So now you have, without even going and doing any tests that might, like development of a drug or whatever, hypothetically, under certain assumptions, you can hypothesize and figure out how effective things are just by running a bunch of numbers. This to calculate those graphs, and this is I'm using here HoloViews to present this. HoloViews is another library that allows you to high-level graphics library that allows you to present all sorts of graphs and overlay them and show them next to each other with a lot of interactivity. This version is not interactive, but there's a lot of interactivity. I'm able to show what happens in multiple scenarios. And here, this is sepsis reducing from 32%. And you can see how other parameters are being affected. Specifically, we're interested to see what happens to ROP. So you can see some of those are noisy. Some of them, there's a clear reduction. So you can actually plot and see what's happening. To do those computations take quite a bit of time on a high performance computing on 64 core machine. But the code for this is available under my GitHub account. Just Google it and you'll see it. Um, Also, I am uh, I, I now want to talk about. Actually, I skipped a little bit. I want to talk about the project that I've been doing for the last 8 years. Um, it's called the reference model for disease progression. I have been uh, I have been working on it for many years. Um, uh, it started by the idea that there is no one disease models. There are many of them, and when there are many of them, then you can actually try to figure out which ones behave better. So let's say the diabetes model, it's a diabetes model, and think about running simulations where each transition has an equation, and those equations you can put that together and get a better model by taking all of those equations and ingesting them. Think about each equation being extracted from a different source, some other clinical trial. Later on, you can do some optimizations in those. So this is the project that I've been working on for many, many years now, and it advances every year. Actually, it has a web page of its own. It's under SimTK, and you can actually follow up and see what's happening with it. Um, I was supposed to actually present something at the NIH about this project. Um, the reference model for disease progression allows you to compare the model to many, many, many populations. What you see here as columns, those are names of clinical trials. Each one of those circles is a cohort within the clinical trials, the treatment cohort, the placebo cohort, or something. I combine them all and call it a different cohort. And you can actually go and see some of the information about this population if you go and circle all of those. What does the reference model do? It takes multiple equations that try to explain what happens to those models. And initially, those are heart attack equations, those are stroke equations, those are all death equations. And the system tries to optimize it and tries to figure out what will fit best all of those populations. And you see this circle over here? This is the fitness that tells you how well it fits. So if you go and slide, you see within each iteration, the system more or less improves the model. And the mixture of models that you see here changes. So now equation number 11 for MI disappears completely. The system tells you it doesn't fit the data. However, some of the equations, like equation number 5 and 6, they fit the data very well, and therefore they become dominant. The same thing you can do what happens with stroke. Now the mixture of those models, this is the best model that can be achieved to explain the data. And when you understand the data, you can see the data, the fitness is an error measure. You want this to be as slow as possible. So here, this population here is an outlier. Um, it's actually, there was a bug last year here. It's actually not a bug. It's a different number that was entered, and maybe shouldn't have. And this year I've added several more things to correct it. But uh, when I publish it, I'll tell you more about it. But for now, look at all the points. Most of them drop down, and the entire fitness improves overall. It's not the best, but because we still have a gap of knowledge, and the error, the ability to explain all of those, you can visualize it now. You want it to be as close to zero, but you cannot. It's this scale here is out of 1,000. So let's say some of those you have like 10% error. Here you have like 5. Some of them you're pretty accurate. Some of the populations you can predict what will happen. So it's important now to understand that the more information we collect, we will be able to accumulate it in models like this in the future, and be able to understand how well we understand and improve things up to the point of how much, to show how much we cannot understand, or how much more, how much, how much, how big is our gap of knowledge. So to feed this model, I actually, to feed all of those populations, I connected to a website called clinicaltrials.gov. I'll just show it to you now. And hopefully I didn't misspell it. Yeah, it's correct. This is today how many clinical trials are in it. About 10%, actually a bit more than 10%, have actual results, numbers that you can model. From this number of clinical trials, I narrow down only those with diabetes conditions that I can model, and those are the ones that entered into my model. And you saw like 30 of those populations out of about 300,000. This is how much more you can potentially model in the future. So what you're seeing here now is only the beginning of the beginning. So it's important to understand this. However, when you try to mine clinicaltrials.gov, you find out it's kind of difficult, because everyone who enters a clinical trial there enters it using a different language, which is a problem. So for this, we created a website called clinicalunitmapping.com. I'm going to show you later. But basically, we are modeling, we're trying to extract information from clinicaltrials.gov, and we're using multiple standards. Today, this is a unit standard called CDISC. Today, we have several unit standards there, but the idea is to take all the units of measure and map them properly. Why? Because currently, or at least this is from February last year. In April, it grew up to about almost 40,000 trials, and today in February it was 23,000, almost 24,000. It became even a larger number of different units. Let me explain. This means when someone wrote down the word meters, they can write down as M, big M. They can write down the word meters. You can write M dot, or all sorts of other variations, and they can misspell it. And all of those examples appear. And this is all for many of the units. So to solve the problem, this is work that I did with Joshua Sherez. We created the website. I'll show it to you in a second. We can take the units and try to match them lexically using Python, several Python simple routines and several tricks you can do. But you can actually visualize how well the units match. So for example, participants with a big P and participants with a small p, that's a unit, they are almost the same, but they are not the same as year. And by the way, you see the interactivity here? This is HoloViews. Um, Try it out. It's a Python library, very easy to use. This is a few lines of code just to do this nice matrix with interactivity, really easy. So we created this website, and I'm going to show it to you now. You can actually go online to clinicalunitmapping.com, and you will see units of measure. You have to go through the home, click start, and you'll see lots of units. Those are units that appear in clinical trials. You can actually see in what clinical trial they appeared in, and some of them appear in many clinical trials. Let me show you here. This one appeared in many clinical trials, and you can actually go on the web, and if you click the button, it will show you the clinical trial, and you can see the unit. Now notice those 4 units. It's essentially the same unit, but it was misspelled like 4 times. You can see sometimes division is by column, sometimes by something else. Uh, how do you deal with it? So they created the website for the purpose of mapping, so people can map and say, oh, this unit is this. But essentially, we want a machine to do it. So we already have machine learning techniques that help you figure out the closest units. And you can see these are the closest units it knows, and it will also know which one of those belong to existing standards. So this is an ongoing project. You will find much more information in the about page for it. I don't want to talk too much because uh, it, I've been talking for a long time now. I think it's time to see if we can get any type of question in. I'm not sure how to do it, but we'll try. But I want to remind you why I'm doing this. I'm trying to figure out ways to actually help machines help medicine in all sorts of ways, either the doctor visualizing data easier or uh, uh, by using machine learning to actually machine to understand things like the units or the text of that entered in clinicaltrials.gov. So it's an ongoing process. It will take a long time. A lot of it has a lot of Python in it, and in this presentation, those are like some of the libraries that you've been seeing. These are all Python libraries. And I can tell you, I'm very happy to tell you that the more I go to this meeting at the NIH, the more I hear the word Python all the time. Python this, Python that. So hopefully it was somewhat interested to the uh, to the um, to the Austin Python meetup to hear this as a backup talk. We will try to get back to regular programming next month if possible. If not, we'll hopefully prepare better. I really don't know how well the streaming went, so I'll try to see if there are any questions that I can pull out. And if there are, I'll try to answer them now, and hopefully it will work. I have no idea. Uh, it's kind of difficult to stream alone here. Um, uh, okay, someone said that there was a address. I hope no one went to the address, but Meetup didn't allow us not to put an address, so we kept the old address. So maybe it's something that we should tell Meetup, maybe allow not to put address or put an address that is clearly so no one can reach. But hopefully some of you were able to actually go in online. I see some of you are watching. Uh, I was expecting maybe 4 people. I see more. Um, so if you have any questions, I'll wait for a little while. If I see them appear, and I hope I have these things set up correctly, then I'll answer them. Uh, uh, I don't know how to do this better than ask you for questions on the Meetup page, or if possible on the YouTube channel. It depends which one. I haven't tried to. I haven't tried it, so I cannot before, so I cannot figure out what is the best method. So we'll wait a few more minutes. And okay, so someone says that there was no streaming. And oh, hi Fred. Thank you for telling it's a nice presentation. Uh, if you have any questions or any topics you want me to go over, please go over. I'm gonna hopefully see in this page, stay on this page and see what happens. And I wish we had better streaming capabilities, but it's the first time we're trying it. If you have better ideas on how to do this, please connect to us. If you can contribute better streaming capabilities, talk to us. We're quite open. Um, um, there will be. I'm going to talk about other Python programming we have. We have Tipton these days. He's giving a bi-weekly course on Flask. If you're interested in this, you'll find it under the Python Meetup every 2 weeks. It's on Mondays and it's in Galvanize. You will have to follow exactly to see how we'll continue. Um, okay. So enough about Tipton. I'll tell you about more before. So Michelle is asking if I can state the name of the graphing library used. Um, yes, I'll be happy to. Uh, I've been using several plotting libraries, and they're actually built upon each other. So in the past, many people use something called Matplotlib. It's a great library. I've been using it for years. However, it's not really interactive, and when you put it on the web, it cannot do interaction. So there was a project that was called Bokeh. I will show you the project now. Bokeh. Sorry, Python. Guys, by the way, it just released Bokeh 2.0. So it's a new version. Later, uh, those people, I'll talk about more, but you can interact with them very nicely. Um, Bokeh itself allows you to do all sorts of interactive things. This is where I was showing all of the the data collected for one individual for about 24 hours. This is where I used Bokeh, and it had interactive capabilities. And this does not have interactive capabilities, but I'm looking for examples that do. Here, this hover tool, the one that allows me to go over things, these are interactive capabilities, very, very easy to do. You can see a few lines of code and you're able to say exactly what you want to show in the tooltips. So this is Bokeh. This is the first plotting library. However, Bokeh itself is still very, very basic in the things that it can do. It's like, how should I compare it to? Um, it, it can plot circles, it can plot lines, but it cannot do higher level things like histograms or the plots that I was showing. Also, if you want to put bokeh plots one on top of the other, this is where it breaks. Like you can still do it, but it will take you a lot of effort. So the guys who do this, all of this, the guys who are doing those plotting library now, they're called Holovis, holovis.org. So they took a bunch of libraries, and actually the entire presentation that you saw, I'll show you this again. This presentation, the ability to, this is one HTML page created all by something called Panel. Panel allows me to do those transitions between the tabs and being able to place all sorts of like pictures in one place and graphs in other and texts in other, and actually it supports LaTeX and several other more things. So this is Panel. On top of Panel, um, they also have different libraries. I don't know all of those. GeoViews is for geographical systems. They actually visualizing of geographical systems. Color set basically is what allows you to create control also nice colors. Um, Param is a bit more complicated. You usually don't use it directly. However, if you use HoloViews or Panel, you get those you actually using Param without knowing it because it's built upon it. And what does HoloViews do? HoloViews allows you to um, uh, take pictures and put them on top of each other, or one next to each other, or have a picture and put an arrow on top of the picture to show something. And they have much higher primitives of things. You can do like a plot and then this histogram plot near it with very few lines of code. And the examples here actually demonstrated. Um, all of those are like you can do a grid of plots. very easily. Just say, oh, give me all of the whatever you enter, just give me a grid. If you remember the grid I made here, here I'll show you again. Uh, this grid, this is made with hollow views. This is like things overlaid on top of another, and you can see all of this like A, B, C, D strategy, and the three of those. I'm able to compose this with hollow views very, very fairly easily with a few lines of code, and you can actually find the code for this um, population occurrence models in this website. It's called. Just go to my GitHub and look for PopDom, and you'll find all the code and all what I did with hollow views there. Um, there's and there are examples that explain exactly what things do. However, unless you have a high performance computing or access to a lot of computing power, you will not be able to run this easily. However, it is there, and you can actually see. So you see, create plots is where I use hollow views. Uh, so this complicated plot is made by basically this line, a few lines of code you see here. Um, let's see else what else can hollow views do. Here, hollow views can do. Uh, Actually, I'll show you a newer presentation that shows much more what hollow views can do. Uh, you can look at this video. Actually, it talks about what PyVis is the previous name of hollow views. PyVis is a greater set of graphic library tools that Python supports. HoloViews is a subset of PyVis, but if you go online, you'll find many times when you say PyVis, people mean actually HoloViz. But there are, HoloViz can also take other libraries, like there's a library called Plotly. So HoloViz sits on top of Matplotlib, on top of Bokeh, and on top of Plotly, and it can combine, and it can sit on top of them, so you can actually use primitives from those, and then use them with HoloViews and Panel. So let me show you a different presentation here. It's another presentation. It will take a while to load. While it loads, I see if someone else is asking questions. If there's another question. Okay. No questions so far, so we'll just have to wait until this loads. It's a bit heavy. But here, with HoloViz, I go to the NIH year and I always take and I have an interactive posters. Most people don't have a poster. My posters, you can actually take a picture of this and download. And my posters are on a computer like this. I don't have to carry those large tubes because I show them all using HoloViz. So this entire HTML page is static. You can do it with HoloViz. And you can do things like putting all of those together, like a picture here. You can have HTML here. Uh, if you press on things like here, you can move around. You can show what you're seeing here is actually 25,000 by 25,000 matrix. You don't have enough pixels on your machine to actually show it. But with HoloViz, it sits on top of a raster library, I forgot its name, shader, data shader. So it sits on top of data shader and allows you to compress a huge image and make it interactive, meaning I'm putting my mouse on it and it will show me things. You can actually compare things, and HoloViews allow you to do this. Like when I say HoloViews and HoloViz, HoloViz includes HoloViews, includes panel. HoloViews allows you to do this specific interactive plot, and it sits on top of Bokeh. Actually, behind the scenes, there's also Bokeh there. And you can do it behind the scenes having Plotly or Matplotlib. All of those things are possible. You can do things like tables like here, or this is a neural network being learned, and you can actually go and see which ones are better, and you can do it interactively. You see this nice grid? Wasn't that hard to generate and plot? You can actually find my presentation code online. All of my presentations, you look later, you'll find many of them. If it's an HTML page, if you go to the summary page, there will be always the code is here, the presentation is here, and you can actually go and download and see how I made this. Some of the things I'm not showing everything, but I'm showing a lot of things, and you can actually download and reuse them. Here I'm showing a neural network from the inside while being trained. So all of those people who tell you a neural network is a black box, no, it's not. You can see inside and you can actually see what happens during training, and you can see it interactively. Um, this is after the thought, after being trained, but you can actually go in training and see how well and trained, and it will give you lots of information. And you can do things like this is something that I didn't even program. All of us has it inside, and this is because it's based on Bokeh that has it also inside. I think I talked enough about Holovis. I have an entire presentation about it. Just try to follow it up. And by the way, it's developed in Austin, Texas, a few blocks from where I am currently. So not only in Austin, Texas, but like a good size of the team is sitting here. Just like many other good tools that everyone uses today in Python, they were developed here in Texas, and you may not even know it. So many in Austin, like SciPy, for example, was developed here. NumPy, developed here in Austin. Many, many, many good tools in Python they were developed in Austin. Austin is kind of a Python town, and I'm happy to be here, and I'm happy that you're here as well. Um, let's talk a bit more. I don't know if there are any more questions, but I'm going to talk about a bit more of programming in the Python meetup, what we're going to do. And I'm going to, first of all, go back to the page where I can see, uh, where did I put this page? You'll excuse me, I have to find it. It's here. Okay, so I don't see any more questions, but I'm going to tell you more what you're going to do with the Python meetup. So I'm going to actually show you the page, and this is the Austin Python meetup. Everyone knows it. Uh, I don't see you put any more comments. Let's refresh the page just to be sure. Or questions here. Okay. I don't see a question. So what we're going to do is we are going to go and look at other things that we're doing in Austin Python meetup, talk about them a little bit, and if there will be no questions, we're gonna stop the stream. And I do hope that you'll put some comments online so we can better improve it, because this is today a test. We might need to do a few more meetups online this way, and maybe we'll use other tools, but we need your feedback for that. So please do help us with this. You see the monthly meetup, it will continue. Next month, we'll have something for you. We already have several things scheduled, possibly the things that we're planning for this month. We have to figure out whether the speakers can actually attend a specific date. So this will happen next month. But and let's show all of the events that's going to happen. Um, so the next month there will be a meetup. We'll post details soon, and hopefully we'll know whether we'll be streaming it live or whether we'll be actually meeting in person. And if we'll be meeting in person, hopefully we will. We'll tell you all examples. We'll tell you where and how and what will be all the rules associated if this will happen. The evening of Python coding, we already have Silas presenting. This is next week. It's supposed to be in Galvanize. Galvanize is currently, last time I checked, we're accepting people. So it may be that we will be there live with people. However, this may change. It depends on multiple factors. I hear many things going on, so we don't know. So stay tuned. For sure, we will have an event for you. Either it will be streaming live or will be a hands-on in-person meeting. It's hard to know, but we will have something for you. And Tipton started his course called "Let's Build a Python Blog." Um, last This week was very nice, highly recommended. He goes over a blog that he created, and he goes into details. Give him feedback about what you want to learn, and he will try to um, go and do and improve it for you, and you can put things in the discussion page. um, for the meetup you can always put things in discussions. So this is Tipton, unless you, it's also taking place in Galvanize. However, I'm not sure it will take place on Monday. Ask Tipton. Tipton is open to streaming, so he might stream his event. So we'll see what will happen. Look it up on the Python meetup. However, notice the registration itself. If you actually want to attend and there will be possibility to attend, it will be through Eventbrite, the link here. Last time the registration was full. However, talk to Tipton about anything that you want. Um, I will go back and see if there are any questions. If there are no more questions, then we will complete this stream, and it will be available online if everything worked okay. I hope it worked okay. There's a lot of technical details here behind. If something went wrong, I apologize. We had very little time and a lot of last minute changes before this event. So we're trying to do our best to accommodate you. And I see some people are still online, so yeah, probably didn't do that bad. Uh, uh, let's see. Um, we're gonna go and check, and I don't see any more comments here. And let's check the other. Yeah, okay. Michelle says thank you. Um, I thank you all, for all of you, for watching and staying that long. Uh, I really hope you enjoyed some of what I showed you. I will be posting some links online if someone wants more information. I'm going to show you what I'll be posting. It'll be something like this, and I'll leave it for a second. These are the links to some of the materials I showed you, and you can actually go over them. I'm going to let it be here for a minute so people can stop the YouTube stream and actually be able to view it. And you will see those online shortly. I will post those on the Meetup page. And I thank you all for listening, and thank you for coming online. And I will. Uh, I hope that by next meetup or two we'll stabilize the situation and know how to arrange the meetup so you all can attend either remotely or physically. It depends on what will be available and what will be the situation. Again, I thank you, and I'm saying goodbye. And I will now close this stream.